Imagine you've just finished writing your tiny Python program. For example, print hello world. You click the green run button, and within a fraction of a second, you see the output appears on your screen, right? It prints out hello world. It almost feels instant. But here's the question: what actually happens after you click run? Does the CPU immediately start executing your code? Or is there an entire journey happening inside your computer before that first line is ever executed? Hi, I am Sanjana. In this video, we are going to follow that journey from the single click all the way to the CPU and see how every component inside your computer works together to make your program run. Before we can answer what happens after clicking the run button, let's meet the 5 players involved. Take a look at these cards. On the far right is your code, the instructions you've written. That code is stored on the SSD until you decide to run it. The operating system is like the coordinator. It makes sure everything happens in the right order. RAM acts as the program's temporary workspace, and finally, the CPU is the one that actually executes the instructions. So, even for a simple print hello world, it's not just the CPU doing the work. Every one of these components has a role to play. But there's one problem we need to solve first. Your code is written in Python, and the computer doesn't actually understand this language or any other language to that matter. Now that we know all the components involved, but there's one big problem. Look at the left side. This is the code you wrote in Python. If you're a Java developer, it would be Java code instead. It's written in a language that is easy to understand for humans to read and write. Now look at the right side. This is what the CPU actually understands. Machine instructions, just long sequences of zeros and ones. So here's the problem. Your Python code cannot go straight into the CPU because the CPU has absolutely no idea what print hello means. Something has to translate it into a language that the computer understands. And that's exactly where the next step comes in. Okay, so now how do we solve this problem? Take a look at this middle box. This is the missing piece, the compiler or the interpreter. Think of it as a translator. It takes the code that you wrote on the left and converts it into machine code on the right, the only language CPU can actually understand. Without this translation, your program simply cannot move forward. It doesn't matter if it's one line, 2 lines, or a million lines of code. The CPU still needs everything in its own language, just like we do, right? Now that our code has finally been translated, it's ready to begin its journey inside the computer. But before the CPU gets its hands on it, there's one more component that has to step in. Now that our code has been translated, so what do you think? Can the CPU start executing it now? No, not yet. Before that happens, take a look at the middle box. The operating system steps in and gets everything ready. It creates the process for your program, reserves the memory it needs, and tells the CPU, okay, the program is ready whenever you're free. Now look at the box on the right. Your program has gone from just being a file on your computer to becoming an active process that's ready to run. The operating system has done its job. Now the next question is, where does this active process actually live while it's running? Now take a look at the journey here. On the left side, your program is still sitting on the SSD. That's where it's stored, where you are not using it. But here's the important part. The CPU doesn't go to the SSD every time it needs an instruction, because that will be very slow for it because it's placed very far away. So before your program can run, the operating system loads it into the RAM, okay, which is right here in the middle. You can think of RAM as the CPU's workspace. Once the program is there, the CPU can access it much faster and it can start doing its job. So the journey is simple: SSD to RAM and finally to the CPU. And once the program reaches the CPU, that's where the real execution begins. Alright, A program is finally in RAM. Now the CPU can get to work. Take a look at the left side again. Your program isn't one big command. It's actually a list of instructions, right? A program is a list of instructions. The CPU starts with the very first one. Now follow what happens on the right. First, the CPU fetches the instruction from the RAM. Then it decodes it. In other words, it figures out what the instruction is asking it to do. And finally, it executes it. Once that is done, it goes back, picks up the next instruction and repeats the exact same process. Again and again, it generally happens for billions of times every second. That's how even a tiny program eventually turns into something you can actually see on your screen. After repeating that cycle over and over again, the CPU eventually reaches the instruction that says print hello world. Now the CPU has done all its part. But notice what happens next. The result doesn't just magically appear on your screen. It first goes back to the operating system, which is responsible for handling things like your terminal, display, and other system resources. The operating system then sends that output to the terminal, and that's when you finally see your printed output. It's not just hello world, but whatever output you want. And all of that, from clicking run to seeing this output, happens in just like a fraction of a second. Don't you think so? At this point, you might be wondering, if the computer is doing all these steps, why does it feel so instant? Right? The answer is right here on the left. Modern processors run at a speed of about 4.2 gigahertz. That means the CPU can perform billions of tiny operations every single second. And on the right, you can see why that's important. CPU isn't doing something new each time. It's simply repeating the same cycle, right? 3 steps: fetch, decode, execute. Again, fetch, decode, and execute. It repeats this loop billions of times every second, so even programs with thousands of instructions finish before we can even notice, right? So now it's time for us to put everything together. It all starts with you writing the code. You click the run button and that's where the journey begins. Your code is first translated by the compiler or an interpreter because the CPU doesn't understand your language. I mean your programming language. Then the operating system steps in and prepares everything that is needed to run the program. Next, the program is loaded into RAM where the CPU can access it quickly. Finally, the CPU starts executing the instructions one by one. All of this happens just by clicking a run button. We've covered a lot in just a few minutes, right? But here's the bigger picture you can look. The table contains everything what each component does individually. But together, if you combine everything, that is what makes your program come to life. You can take a look of all of this just for your reference. Now, let's imagine something. What if we just removed one of those components? No compiler? Your code can never become machine code. No RAM? The CPU has nowhere to load your program. No CPU? Nothing gets executed. No operating system? There's nothing to coordinate the entire process. And even if everything else worked perfectly without the output, you would never see your result on your screen. That's the interesting part about computers. None of these components are optional. Each one has a different job, but they all depend on each other. Remove even one of them and the entire journey comes to a stop. If you remember just 3 things from this video, let them be the ones I'm telling. First, your code doesn't run as you write it. It has to be translated into a language that the CPU can understand. Secondly, your program doesn't run directly from the SSD. Before anything happens, it has to be loaded into the RAM, where the CPU can access it quickly. And finally, the CPU doesn't execute the program all at once. It works one instruction at a time, repeating the fetch, decode, and execute process. Once these 3 ideas click in and you understand them, you've almost understood the foundation of almost every program runs on your computer. So now you know what happens after you click run. Your code gets translated, operating system prepares it, and the rest of the story. But there's one question we've not answered. Why does the CPU only understand zeros and ones? Why not Python? Why not Java? Why can't computers understand the same languages that we write? That's exactly what we'll explore in the next video. If you like my video, please consider subscribing to my channel because I will come up with such interesting videos every alternate days. Thank you for watching.